Alright, let's begin. Alright, kia ora everyone. Here's your first lesson of the week 8 lockdown. I want you guys to note on the bottom that this is actually lesson number 16 and 17. I've decided to combine it together because lesson number 17 was really just a study lesson, but I did integrate some new information in there. I don't normally teach that information with this one because it is kind of a lot to digest, but I figured I don't see a point in making a lesson 17 video because it would have been very short, so I'm including it in this. So just keep that in mind. Anyway, so today what I want to do is talk about how we process using Hess's law. It's basically the second type of calculation you're going to get for your thermochemistry exam. So basically, we're still looking at that enthalpy material, and then the other thing we're looking at is using Hess's law and its related calculations. There's basically two ways I'm going to show you it for today. Cool. So here is Hess's law as an overview. So the first law of thermodynamics is saying that energy in a system is always conserved. Energy is not created or destroyed. Remember, it's merely just transferred. Hess's law, then, is stating that enthalpy change is due to a chemical reaction, and that is independent of the route taken. So what that means is, even if I'm not talking about the specific route in question, if I can combine different equations together that the net result is the same equation, then I can use that to then determine what this other original equation that I want to calculate is. So, yeah, basically, in dummy terms, it means that if I don't know the enthalpy of a reaction, I can find it by manipulating other reactions that I do know the enthalpy for. So let me show you guys some ways we can manipulate these equations. So here's my original equation here. It's the combustion reaction for propane. And the forward reaction tells me that the enthalpy value is that negative 2220 kilojoules per mole. Now, if I reverse that equation and I go from carbon dioxide with water and I'm making propane and oxygen, reversing that reaction, all I need to do is change the sign of my enthalpy. So we can flip equations when we are doing Hess's law. All we need to remember to do is change the enthalpy sign, and you're fine. So that's the first way we can manipulate it. The second way we can manipulate it, and in this case we're looking at the combustion of carbon, is I can multiply that equation by a factor. And when I multiply that equation by a factor, I also multiply the enthalpy by that factor. Really useful, again, when I'm trying to manipulate equations and cancel things out, because I can multiply the equation that I'm trying to manipulate to basically get the net equation that I want. So basically, the sign still stays the same. I multiply it by 3. If you do both, then you multiply and you swap the signs. When I say both, I mean flip the equation and multiply it by a factor. So let's keep calm because it's time to do some math. So I will go through one of these questions from the ESA guide and show you how we manipulate it. And then I'll show you an alternate way you can do that, but that is really, really specific. So let's do that first one. All right. Again, it's going to be really useful if you annotate the question. So, first thing that we are looking at is I have been given a list of different reactions. So, the smelting of iron ore involves the reaction with zinc and the zinc sulfide with oxygen gas with the following equations. So, we have the combustion of zinc, we have the combustion of zinc sulfide, and then they've also given us, using the following information, the data above, we also have the combustion of sulfur, making sulfur dioxide, and they've given me the enthalpy value. All of that is going to show you the equations that you're going to manipulate. They want you to calculate the enthalpy change for this reaction here, the zinc with the sulfur becoming zinc sulfide. So that is actually what I'm trying to get. I like to make it really clear what my aim is. So my aim is I want this reaction, zinc plus sulfur, making zinc sulfide. So everything I'm doing is in reference to making that as my final equation. Some things I want to note for you guys: make sure you're checking your states. It's not going to be so important for this equation, but every so often you're going to have maybe water in the equation, and in some equation the water will be gas, and in some equations the water will be a liquid. And what they might then include is, as part of the list, the say, for example, the enthalpy for the fusion of water and the enthalpy of the vaporization for water. So basically, a state change equation will be provided for you. And you also need to factor that in if there is anything, when you're manipulating these equations, that's going to result in if you having to go from, say, for example, a liquid to a gas with your water. So do keep that in mind. It's often kind of snuck in there, and it's usually used as like an excellence level kind of point to see if you caught the phase change component to it. In this case, that's not going to be a problem because when I look at it, everyone's still in the same state. So zinc is constantly in the solid state, sulfur is in the solid state, oxygen is in the gas state, sulfur dioxide gas state. So there's nothing in here in my list of equations that they've provided for me that states you need to think about a phase change, because there's no equations here that have a phase change in them. So that's usually a good hint that you might need to use it, is if you see any phase change equations as given as part of your list. Anyway, what I like to do is I like to go through each one of those equations and I basically identify what I need from each equation. So for this first equation, I will need the zinc. From the second equation, I want the zinc sulfide. And then from the third equation that was provided, I want the sulfur. So those are the three components. Everything else here will eventually cancel out when I start manipulating these equations. So first thing I'm going to be looking for is it on the right side of the equation? So zinc is on the reactant side, so that one's fine. Sulfur is also on the reactant side, so that's fine. The zinc sulfide, however, is not on the right side of the equation, so what that tells me is that I'm going to need to flip this one. So that way when I flip it around, the zinc sulfide is now on the product side that I need. So if I'm doing that flip, I need to change this sign to now being a positive. The other thing I'm going to be checking is, do I need to do any sort of multiplication to cancel things out? So when I look at that main equation, they're all 1, 1, and 1. So that tells me that these equations could all stay the same. But I might need to multiply them out whenever I'm doing some of the canceling. It's unlikely. In most cases, you're going to be doing your multiplication step quite early. So now that I know all my equations, what I'm going to do is I'm going to write them each down. I'll do them in different colors to help you kind of distinguish which one's which equation, and then I'm going to be adding together the enthalpy values from basically how it's been manipulated. So this first equation is zinc with half oxygen making zinc sulfide. Again, line everybody up so that way it's really easy for you to see them. Sorry, I was just thinking about I was teaching redox to my year 12s, and I was telling them about equations and lining it up, and I just remembered I haven't told you guys about that. So I always find it really useful if I line my arrows up, so that way it's very clear what's the reactant side and what's the product side. So I'm writing down zinc. I'm writing down 1/2 oxygen, which is a gas, and I'm writing down my zinc oxide, which is a solid. So that's my first equation. The other thing I like to do is keep a running tab of the number. So I haven't done anything to change that equation, so I'm keeping that negative 348 kilojoules per mole. Cool. Second equation then. I have my zinc sulfide reacting with oxygen. Now I've noted that I wanted to flip it, and that's precisely what I'm going to do. Put my arrow down, and I basically flop everybody around. So zinc sulfide is going on this side. The 3/2 oxygen is going on that side. That's a gas. Remember, that 3/2 just basically means 1.5. If you guys don't know your fractions. And then the products are now going to go on the reactant side, because like I said, I flipped this equation. So that's going to have my zinc oxide, and that's going to have my sulfur dioxide. Now, we can already see that things are going to be set up to start canceling, because I see that my zinc sulfide's on my reactant side here and on my product side here. That's going to eventually cancel out. But we'll do that as our final step. So I have flipped that equation around, so my enthalpy for that has changed. That's going to be positive 4, 4, there we go. Positive 441 kilojoules per mole. Cool. All right, last one that I'm doing is that zinc, that sulfur and the oxygen. So sulfur plus oxygen is making sulfur dioxide, and that's a gas. I've done nothing to manipulate that equation, so I just copy down my enthalpy, which is negative 297 kilojoules per mole. So I'm keeping basically a running total of how I'm manipulating everything. All right. Last thing I want to do then is I want to put everybody together, and I'm just going to check to make sure everyone's canceling out and that my net equation is exactly the same as my original equation. So we're just going to go back to the red, because that's basically what I'm trying to hopefully get in my final equation. So let's look at that through. So as I'm going through it, zinc, I look on this side, nothing over here is zinc, so that one's going to remain in my final equation, which is what I want because that's going to be on the top over here. The sulfur in this case, or sorry, what am I doing? Oxygen is a half here, and I see that I have one oxygen here, and then on this side I have 1.5. So that oxygen, when we add those two, will cancel with the one on the other side, because that's 1.5, and that's also 1.5. So I'm not copying the oxygen down in my final equation. All right, next thing I have is my zinc oxide. Well, I have zinc oxide on the reactant side of this second equation, so that zinc oxide will cancel, so I'm not writing that guy down. All right, sulfur dioxide I have on that side, and I have on that side of the equation. They're the same number, so those are both going to cancel out, so I'm not writing the sulfur dioxide down. Then I look, I'm going to have my zinc sulfide. Zinc sulfide's not on that side. It's also included in my original equation, so I'm writing that one down. And then the last equation, both of those things have already been canceled out. All I have left is my sulfur. So I'm writing that guy down, which is, again, part of my original equation. So what I can see is that my equation that I've gotten through using Hess's law is the same as the one that I was trying to solve for. So that means that I have done my working correctly. It's really useful to do that as a double checking method. This is usually a very easy excellence point if you don't make any silly mistakes. All right, last thing I now need to do then is add all those values together and get the enthalpy for this reaction. So my delta RH is going to be equal to, so I'm going to do negative 348 plus 441 minus 297. So I have negative 204 kilojoules per mole. Make sure you have your units. Make sure you have 3 significant figures. Very often with these sort of questions, having the right answer with the significant figures and the units is the excellence, and then the merit is basically you forgot significant figures or you forgot your units, or you have a mistake in your units. So really silly way to lose an excellence point. But if they make it kind of trickier and they include a phase change, usually then the phase change inclusion is the excellence, and forgetting the phase change is going to drop you down to a merit. Anyway, that's that first question. So let's go back to the PowerPoint and let's talk about the alternate way you could do this. So there is another way to use Hess's law, but this is really, really specific. This only works if everything that you have been provided is enthalpy values for formation equations. So basically, you can't have anything that's a mixture of stuff. So the last calculation we couldn't use it for because when we look at it, this one here is a combustion equation, this one here is a combustion equation, this one here is your only formation equation, so we can't use this version for what we're doing. But we can if all of my reactions are formation. When that happens, I can just identify what is reactant, what is product, and then do a quick little subtraction step factoring in any multiplication for multiple factors if I need to manipulate it. So let's see another example with their little shortcut. Cool. All right. So they want me to calculate the combustion of ethanol. So this is my goal equation here. Sorry, that was really messy. That's my goal equation here. And they have given me 3 different reactions. My first reaction is this one here, my second reaction is this one here, and my third reaction is this one here. Now, what I'm looking for is that everybody is an F, so everybody is a formation reaction. I can use my shortcut. Now, what you're going to do with this is you are going to be checking to see where are these different components located, and are there any multiples, because then you need to quickly do a multiplication or change of sign for that reaction. So, formation of ethanol. So remember, with the formation equations, these guys are all being shown as products. So when I'm looking at this, ethanol formation, that's giving me a value here. When I look to see where ethanol is in my reaction, actually, let me do that in blue so that way we're following each color code. I can see that's on the reactant side. So what that tells me is I need to change the sign. The other thing I check to see is what the ratios are like. So this here is 1, so that can be left alone. Remember, with all the formation equations, these guys are already 1 mole. I know that. I don't need to do any of the equations to double check it, because whenever we do formation equations, it's always in reference to the product being 1 mole. So we just keep my working. So I'm going to write positive 278 kilojoules per mole, and that's from that first bit when I'm looking at my ethanol. Cool. All right, second one is I'm looking at the formation of water. In this case, water, like I said, all these formation equations, that's a product, and I see that water is a product in this reaction, so I don't need to flip it around. But I see that this is a 3. So what it needs to do then is I need to multiply the enthalpy by 3. So that would be 286 times 3. Remember, there is a negative sign there, so that would be negative 858 kilojoules per mole. So that is what I'm going to use over here. Add that to my running total. It's basically, like I said, it saves you time because now you don't need to write out all these equations. You don't need to double check to see how the equations are being manipulated. You can just do the shortcut with using their enthalpies. All right, last one is the formation of carbon dioxide. Again, I look and I can see in my equation that carbon dioxide is a product. The formation of carbon dioxide would also be the product. So no change to the sign. I do, however, see there's a 2 in front of the carbon dioxide, so I do need to multiply that by 2. Whoops. And so I get that this value, 394 times 2, is negative 788 kilojoules per mole. So again, I keep that to my total, negative 788 kilojoules per mole, and that's referring to the carbon dioxide. Now, you might be wondering, what is going on with this oxygen here? Why don't I have anything that I need to add to it? The reason why I'm not doing anything with the oxygen and there's no equation or there's no enthalpy for the formation of oxygen listed is because the formation of oxygen or anything that is an element is 0. So that's why that's being ignored. So at this point now, I can put everybody together and figure out what my enthalpy value is. So 278 minus 858 minus 788 equals negative 1368 kilojoules per mole. Now, in this case, I would be getting a merit because I don't have my significant figures. And if I want, I can be extra fancy and say, look, I know the combustion enthalpy of the ethanol in the liquid form. Will be even more specific. That's a very bad looking L. Is equal to negative 13, and we're going to round that up to 70. So now that's 3 significant figures, kilojoules per mole. And that's the shortcut. But like I said, the shortcut only works if everything you have is given in formation. If it's not given in formation, then you're going to need to do what I did in that first example. And like I said in last week's lesson, all this stuff about formation and combustion equations and writing them out will come into play now. So sometimes they're nice and they give you the equations. Other times they won't be nice and you'll have to figure out the equations yourself as part of the steps. But yeah, that's what you're looking at for the second type of calculation. Personally, I think the Hess's law is easier than the ones you were doing last week, because I feel this is less tricky. Like, there's less language that you need to kind of understand. You basically just need to go through and go, how am I manipulating everybody? Cool. All right. So, Kapai, really good work today. So today you learned how to use Hess's law. Follow that up with, lesson 16 and number 17. I think on the Google site I have it listed as 16 and 17 on there. And then make sure any work that you're doing you insert into the evidence of week 8 lockdown work.